Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of organic chemistry lectures and solutions to homework problems. In this Scribblecast lecture, we're going to be taking a closer look at bicycloalkanes. One might wonder why we're looking at bicycloalkanes in the alkenes section. Well, if you recall, last lecture we looked at 1,2 and 1,4 electrophilic additions to conjugated dienes. We defined the terms kinetic control and thermodynamic control. We then looked at the Diels-Alder reaction and discovered that a diene can actually undergo reaction with a dienophile to produce ring structures. It is because that the Diels-Alder reaction can make bicycloalkanes and alkenes that we're interested in looking at these types of molecules. For example, suppose I had the following conjugated diene. And I reacted it with this alkene. Apply a little heat, and I could get a Diels-Alder reaction taking place, where those pi electrons go there, these go here, and these pi electrons attack there. What I would get would look like this. The edge on view would look something like this. Okay, now there's a pi bond here. If we then hit this with H2 gas and platinum, a catalyst, we could hydrogenate this molecule and produce this. Or again, the edge on view would look something like this. There we go. So you get an idea of what a bicycloalkane looks like. What are bicycloalkanes? They are saturated hydrocarbons, such as this molecule. Saturated hydrocarbons with two rings and two or more carbons in common. These common carbons are called bridgeheads. So if I make it a little larger, the bridgehead carbons that are common in this structure are here and here. These are the bridges, bridging carbons that join and connect the bridgeheads. So in this bicycloalkane, we see two bridgehead carbons joined by three bridges. Okay, we're going to come back to this molecule and take a closer look at it. But bicycloalkanes can be generated from alkenes through the Diels-Alder reaction. And we need to expand our nomenclature to include them. How do we name a bicycloalkane, including numbering it? Well, let's draw a bicycloalkane with different size bridges. In this case, we have all the same number of bridges. But if we really want to explore the rules, we need different size bridges. So what I'm going to do is draw a bicycloalkane. That looks like this. To number a bicycloalkane, you must start at a bridgehead. So find your bridgeheads, and I'll put a dot on the bridgeheads. The bridgeheads are the common carbons joined by all three bridges in the bicycloalkane. To number, so let's blow this up a bit so it's a bit easier to see. There we go. So here's my bridgehead carbons. All right. So if we want to number the bicycloalkane, we start at one bridgehead and number around the longest chain or the longest bridge. To the other bridgehead. Then continue on around the second longest chain. Back to the original bridgehead. And then finally, across the shortest, I'll just say the short bridge. So basically you're numbering from bridgehead to bridgehead. So you start at the bridgehead, 1. Would I start at this bridgehead? Well, I would start at the bridgehead that ends up giving me the smallest number for a substituent. But in this case, since there's no substituents, it doesn't matter. So I must go through the longest bridge first. That's a rule. It doesn't matter if there's a priority group on a shorter bridge, you always go through the longest bridge first. So 1, 2, 3, 4, 5. Then I continue 6, 7 through the second bridge. Notice I continued from 5. And then I go from 1 to the next bridge, 8. Now I've numbered every position on the ring. So if a substituent appears, I can use that number to localize the substituent. Okay? Now, if there was a substituent, say, here. Let's say we had a methyl here. I could have numbered if there's a methyl here, 1, 2, 3, 4, 5, 6, 7, 8. And notice the difference between a 2-methyl and a 4-methyl. The 2 is better. So numbering from this bridgehead would have been better. Okay, but let's get rid of the methyl and just go on with the naming of an unsubstituted bicycloalkane. All right, how do we name it then? Well, to name it, 1, we use the prefix bicyclo. Just like cycloalkanes begin with the term cyclo, bicycloalkanes begin with the term bicyclo. We then use square brackets. Inside the square brackets, we put numbers for the number of atoms in each chain. We put them in descending order and they're separated by periods. Okay? So for example, I would begin, if I was naming this guy, I would say bicyclo. And then I'd put square brackets right beside there. And the longest bridge has 3 carbons. So I'd say 3. Period. The next biggest bridge is 2. Period. Next biggest bridge is 1. Now if there was no atoms in a bridge, I'd use 0. Okay. The parent name representing the total number of atoms is then used. Use the parent alkane name. We don't need cyclo because we've got bicyclo. So now we just count the total number of carbons and figure out what it is. Well, we have 8 carbons. 8 carbons is an octane. This is a bicyclooctane. A bicyclo 3,2,1 octane. The name's very easy to generate. What's interesting is when given this name, it's very easy to draw the alkane. Suppose you were given this name. How would you generate it? Not hard at all. Bicyclos have 2 bridgehead carbons, so here are my bridgeheads. 3,2,1 means 3 carbons, 1, 2, 3. And then I can do a 2, 1, 2, and then I can do a 1. Notice that generates the same structure we had previously, where I just put in 2 bridgeheads, and then this just told me the numbers. I can check then by counting up the atoms. 1, 2, 3, 4, 5, 6, 7, 8, that I have a proper octane. Okay, let's try applying some of this nomenclature to various bicycloalkanes. And then we'll apply it to the one we made in our Diels-Alder reaction. Here is an interesting bicyclic. How would you name something like this? This is the molecule from our molecular models lab, which was called Decalin. Decalin is a common name. The bicycloalkane nomenclature I've given you is IUPAC. Decalin would be its common name. So, what is, okay, so that's common. What is the IUPAC name? Well, the IUPAC begins with bicyclo. And now I number the bridges. Here are my bridgeheads. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 atoms. This is a decane. Number your bridges. 1, 2, 3, 4. On the other side, there's also 4 atoms. So this is a 4, period, 4, period. Now, the third bridge. How many atoms are in the third bridge? Well, the bridgeheads are directly bonded. There's no atoms in between them. There's no bridge. Hence, it's a 4, 4, 0. With 10 carbons, it is a decane. No spaces. That's the IUPAC name. So in fact, what we can do is we can go through a whole list of alkanes and give you both their common names and their IUPAC names. Yes. Let's start with this guy. Now sometimes they're drawn flat. Like this molecule. Could be drawn this way. Sometimes they're drawn edge-on. There are my bridgeheads. This molecule, what is it called? Well, it has a common name, Norbornane. Norbornane. Norbornane's IUPAC name is bicyclo. Count the bridges. We have 2 carbons here, 2 carbons there, and 1 carbon at the top. So this is a 2, period, 2, period, 1. How many carbons? Count the bridgeheads. Don't forget to count the bridgeheads. 1, 2, 3, 4, 5, 6, 7. This is a heptane. A bicyclo 2,2,1 heptane. Interesting. What if there was a double bond? Here. The common name for this molecule is Norbornene. Norbornene has the double bond in this position. Notice it's identical if the double bond were here. Common name is Norbornene. What's the IUPAC name? Well, it's the same thing. The bridges haven't changed. It's Bicyclo. 2, 2, 1. That hasn't changed at all. But now we have to number. Notice if I'm numbering along the longest bridge, 1, 2, 3, 4 would not be the numbering I would use, because then an alkene would appear 5. Since they're both 2-carbon bridges, I get to choose which bridge I go around. Now, yes, if this bridge was bigger, I'd have to go around it first, but it's not. 1, 2, oops, 1, 2, oh yeah, 3, 4, 5, 6, 7. So we see this is a 2-heptene, or heptene. Well, obviously, the next one, related to this, and because it's related to this, I'm going to just put in the double bonds here. What if there's 2 double bonds, here and here? Well, then we've got a molecule called Norbornadiene. That's its common name, Norbornadiene. Norbornadiene has a IUPAC name of Bicyclo 221 hepta. Now let's number it. 1, 2, 3, 4, 5, 6, 7. We have double bonds at 2, 5, so hepta 2, 5 diene. Hepta 2, 5 diene. Right. Let's put a substituent on Norbornene. What if we had a substituent? So I've tilted this. It's kind of a poor drawing. Let's see if I can fix that. Great. So these bonds are closer to you. That's why I make them a little thicker. So here's Norbornene. Now suppose, notice there are 2 positions here. If there were hydrogens, I'm going to draw on the hydrogens. There's one hydrogen that goes out here, and there's one hydrogen that goes down like this. Suppose I put a substituent here. Okay. Suppose I place the substituent in this position. This chlorine is out and away from this cyclopentadiene ring. Because of that, this is called exo. Also, because it is on the same side of the peak carbon pointing up, exo is also cis. So exo and cis are the same, and you can actually use these 2 names interchangeably. But in these bicyclics, I will mark you on using exo, even though cis is acceptable. How would you name something like this? Well, just like if you had cyclohexane with a chloro substituent, you name cyclohexane in the root, and the chloro comes up front as a prefix. So you'd say 1-chlorocyclohexane, for example. In naming this molecule, you do the same thing. If you're using the common name, you would say exo, and now we could number this. Numbering would go this way: 1, 2, 3, 4, 5. Why this way? Well, the 2 is the lowest possible number for the alkene. Notice I only can go towards the alkene because this is also 2 carbons. If there was a 3-carbon bridge that didn't have the alkene, I would go around the 3-carbon bridge first and then give the lowest number to the alkene possible. All right. So I've got 1, 2, 3, 4. It's a 2-ene. Well, this molecule's common name is Norbornene. The chlorine's at 5. I could say 5-chloro-norbornene. If it says give an acceptable name. If it says the common name, you'd have to give this. The IUPAC name is exo 5-chloro bicyclo and then we've got 2, 2, 1. And of course there's no space, right up against the square brackets would be. We've got 6, 7. We have a heptene at 2, so hept 2-ene. And this would be right beside those brackets. That's the IUPAC name. If we had switched, if this was the H and the chloro was down, now the chloro is pointing into the ring. And hence it wouldn't be exo, it would have been endo. And endo is equivalent to trans. So in bicyclics we use endo and exo for substituents. Here's another ring structure. That's very interesting. Molecules with cyclopropanes on them. This molecule, remember, can be formed by taking cyclohexene and reacting it with CH2N2 in light. Because this makes carbene or methylene, and you put a cyclopropane. This molecule's common name is Norcarane. The IUPAC name is bicyclo. Find your bridgehead carbons while they're here. There's your bridgeheads. Number along the longest carbon chain. 1, 2, 3, 4. There's 4 carbons. The second longest has 1 and no carbons on the third. So this is a 4, 1, 0. Bicyclo 410. Now I can number all the carbons, 6, 7. This is a heptane. A bicyclo 410 heptane, alias Norcarane. Notice if there were substituents off this peak, like 2 chlorines, I would have to put a 7,7-dichloro in front of the bicyclo. 7,7-dichloro, then the bicyclo. 410. Ooh, don't know if I can fit it. Ooh, running in trouble. Made it. 7,7-dichloro bicyclo 410 heptane. Why 7,7? you must number around the longest chain first, the longest bridge. It wouldn't matter if there was a double bond O there. Oh, let's do that. Let's put a double bond O there. What if it was this? Well, then that would be bicyclo 410, what? Heptane 7 one. Ketone's highest priority gets in the root, just like a cycloheptanone. Interesting. Fascinating. What if we had some substituents on our Norcarane? How about, ooh, let's try some cyanides. Actually, you've skipped the cyanides. Let's try a different molecule. Let's go back to the molecule we originally were going to name. We had two molecules, remember, in our reaction. Let's draw a reaction again. We took cyclohexadiene plus an alkene, ethene, applied some heat, did a Diels-Alder reaction, and we made this guy. So those are my bridgeheads. And we had an alkene here. We then went on and hydrogenated it. In the case of H2 gas and platinum, getting rid of the okay, so here's my bridgeheads. Name this molecule. Well, he would be bicyclo. Two. If I count up the carbons, 1, 2, 3, 4, 5, 6, 7, 8. Octane. One, two. This guy would have been bicyclo. Two, oct, 2 ene. Okay, there you have it. Let's try one where a high priority group doesn't appear on the longest chain, and it can be a little tricky. Let's go back to our original one. Put a double bond here. How would you name that? Having trouble drawing a straight line. How would you name that? Well, again, we begin with bicyclo. The alkene ends up in the root. I must number from the bridgeheads. 1, 2, 3, 4, 5, 6, 7, 8. I have a bicyclo, a bridge of 3, a bridge of 2, a bridge of 1, and a heptane. How's that look? What's wrong with that name? What's wrong is you numbered through a smaller chain. You have to, absolutely have to, number around the longest chain first. 1, 2, 3, 4, 5, then 6, 7, 8. I can check whether numbering the other way would give me a lower number for the alkene. I could go 1, 2, 3, 4, 5, 6, 7, 8. That will work just as well. But the alkene ends up at carbon 6 no matter which way I go, so it doesn't matter. And so this is a heptane. Watch that. You must number around the longest carbon chain first. Well, this was a shorter Scribblecast lecture. If you have any questions about this nomenclature bicycloalkanes, please see me at the end of class. I'm Dr. Brian Lloyd. This is my Scribblecast lecture. Thank you very much.